All right, on to what students probably think are the most difficult reactions to write equations for. There's a lot of stuff going on here, I guess, so just be careful. Gas formation reactions, these are a type of double replacement reaction. These are not redox reactions. And so here are the gases. There's three of them. At least there's going to be four gases that we'll talk about. Four gases that can be produced in a double replacement reaction. First one is the formation of carbon dioxide. And so what I'm going to write in the notes is the net ionic equation for the reaction. So here's how it works. Anytime you have a carbonate or a bicarbonate, it's either one actually, carbonate or bicarbonate that reacts with an acid. Doesn't matter if it's a strong acid or weak acid, binary, ternary, doesn't matter. You always produce carbon dioxide, water, and another product. Let me show you the net ionic equation. So make sure to add to your notes too, it could be a bicarbonate. So things like sodium carbonate, calcium carbonates, lithium bicarbonates. Remember, bicarbonate is HCO3 -1. Reacts with an acid. And again, here I'm just showing net ionic equation. We have just H plus written here, so I guess this would be for a strong acid, but it doesn't have to be. You make carbon dioxide, water, and then whatever the anion of the acid is and the cation from your carbonate or bicarbonate will produce your other product. So for example, if you have sodium carbonate that reacts with hydrochloric acid, in fact, let's write that equation. So again, think of this as just regular double replacement type reaction. A lot of times students want to do this though. So H goes with CO3 to make. Please, please, please never, ever, ever do this. So the carbonic acid, if you will, that is produced spontaneously decomposes into water and carbon dioxide. So we get in this reaction, sodium chloride is produced, that's our salt, with water, and the main thing here, we're producing carbon dioxide gas. And again, one more time, this could be sodium bicarbonate reacting with hydrochloric acid. Any carbonate or bicarbonate with any acid will produce carbon dioxide gas. Next one is the formation of sulfur dioxide gas. Sulfur dioxide gas forms in the reaction between, again, it says here, an acid. So all of these reactions involve an acid with some ionic compound. In this case, the acid reacts with a sulfite, doesn't matter what the cation is, or even a bisulfite. Bisulfite being HSO3 with a -1 charge. So again, very similar to the reaction above where you produce carbon dioxide. Same idea here, you get three products. The gas that is produced is sulfur dioxide. Next one's a little bit different, formation of hydrogen sulfide gas. This gas is responsible for the smell of rotten eggs, so it's a rotten egg smell. This gas is produced in the reaction between a sulfide, so be careful, sulfite versus sulfide, sulfide with an acid. This time we only get two products, so there's no water produced in this reaction. So for example, if you had sodium sulfide reacting with, I don't know, hydrochloric acid, we'll say that's fine. You produce hydrogen sulfide gas, and in that case you'd produce sodium chloride. Again, the cation from the sulfide, anion from the acid makes your other product. And then we have one double replacement reaction that produces a gas, this time when something reacts with a base. So it says when a base is added to an ammonium solution, so in this case the anion doesn't matter, so some ammonium containing substance with a base. Here we're talking primarily an Arrhenius base, something that has hydroxide. So here's the net ionic equation. So let's say you had ammonium chloride, solutions of ammonium chloride and sodium hydroxide that are mixed. So we have the ammonium and hydroxide reacting to produce your gas, ammonia gas, water, and then in this case we have the cation from the base and the anion from our ammonium salt to produce the other product, in this case, which would be sodium chloride. If you take a look on page 157, there's a very extensive table summarizing all of the reaction that we've covered, including, I believe, combustion, which we haven't talked about in the notes, but we've talked about it before. So please refer to that if you need assistance on keeping track of what type of reaction it is between different substances. So very, very useful table. It's got them all there. All right, turn to 156. Let's look at some examples. What's really important when you're writing chemical equations for a reaction is to identify the type of reaction. So is it a synthesis? Is it single replacement, double replacement, combustion? That way you can predict your products. So I'm not going to have you do it on your homework or on any sort of quiz or test, at least not in the near future. I will, I think, later on. But it's a good idea to write down what type of reaction it is before you attempt to write a balanced equation. So that's what 415 is asking you to do, the type of reaction. So here's what we do. Letter A, I see an element reacting with a compound in solution. This is a single replacement reaction. Letter B, what I see there is just one reactant. Anytime you have one reactant, that has to be a decomposition reaction. Letter C, same thing. Again, we have one reactant. We see that heat is being applied. That's another key to be careful with decomposition and combustion. You're heating it up, not necessarily in the presence of oxygen. It's not reacting with oxygen. It's just breaking apart, so decomposition again. Letter D, we have a double replacement reaction. So we have two compounds in solution that are being mixed. Specifically, this is a precipitation reaction. Letter E, we have one product. So if you take two things and combine them to make one thing, that is a synthesis or combination reaction. And then letter F, two compounds in solution. This time we have an acid reacting with the base. So this is a double replacement reaction, specifically a neutralization reaction. And we can certainly do more examples in class if you like. Just let me know. All right, so last type of reaction, these involve anhydrides. The word anhydride here means without water. These are the metal and non-metal oxides. So we'll start off with the metal oxides. They go by another name. Actually, there's a couple names they go by. So let me read you what happens, then I'll give you the names. When placed in water, these substances, metal oxides, form basic solutions. Consequently, they are known as basic anhydrides or also basic oxides. So any metal oxide, when you put it in water, produces a basic solution. We call these basic oxides. Let's take a look at an example between the reaction of sodium oxide. Again, be careful, not sodium hydroxide, but sodium oxide and water. When sodium oxide reacts with water, we form a basic solution. Any guesses what base forms? It will be sodium hydroxide. Go ahead and balance the equation, and then we're going to complete this. We're going to write the ionic and net ionic equation for this reaction as well. Let me put in states of matter first, and then you balance it. Sodium oxide is an ionic compound, it's a solid. Our sodium hydroxide is now in solution because of the water that was present before the reaction. Pause the video and balance the equation. All right, let's go ahead and write the ionic equation. So sodium oxide is a solid, so it's not yet in water, so we do not want to show it dissociated. Water is a liquid, so it does not ionize, so we should leave it as H2O. Now be careful, the next part, sodium hydroxide. Does it ionize in solution, or does it dissociate in solution or not? Well, what kind of base is sodium hydroxide? Sodium hydroxide is a strong base, so remember, for any strong base or strong acid, when writing ionic and net ionic equations, we show them dissociated or ionized. Next step is to write the net ionic equation. So to do so, we need to identify any spectator ions and eliminate them. So what is the spectator ion in this reaction? There are no spectator ions. So the net ionic equation in this case would be the same as the ionic equation. All right, next we have the nonmetal oxides. So you could probably predict what's going to happen here. When placed in water, these substances form acidic solution. So these are known as acidic anhydrides or acidic oxides. So again, any non-metal oxide will react with water to produce an acid. Let's take a look at an example, reaction between sulfur trioxide gas and water. This is significantly more tricky than the previous example. So here's the deal, and I don't know if it comes up now or later, so I'll mention it now. In this type of reaction, it's very important that the oxidation state of the nonmetal is the same before the reaction as after the reaction. So there's several different acids that have sulfur in them, and so they're all binary. So let me give you some options, and then we'll see if we can identify the correct one. So essentially, these are our options. Again, all the sulfur-containing ternary acids are diprotic, which means they have two hydrogens. I think I said binary before. Diprotic, two hydrogens. So here's your options. So go ahead and pause the video, identify the oxidation state of sulfur in SO3, and then find the correct formula where sulfur has the same oxidation state as in SO3. Go ahead and pause the video. In SO3, sulfur has an oxidation state of +6, and the formula written to the right side there that also has an oxidation state of sulfur of +6 is the H2SO4. So let's erase all that other stuff and write our equation. So here's our balanced equation, including states of matter. Go ahead and pause the video and write the balanced ionic and net ionic equations for this reaction. Pause the video, please. Did you remember that even though sulfuric acid is diprotic, it is only strong for the first proton that it donates? So again, first thing is that sulfuric acid is strong, so we need to show it completely ionized in our ionic and net ionic equations. But it does not dissociate, it does not ionize into two H pluses and one SO4 minus 2. It's got to be this way. We mentioned this in the previous video, so be careful with sulfuric acid. And just like our previous example, the ionic and net ionic equations are the same, and so we can just leave it at that. All right, this concludes this lesson. Again, if you would like to do some more examples in class, please let me know. We can do whatever you want. I'll give you lots of practice in the meantime. All right, thanks for watching.